All right, hello and welcome. Today we're going to do something a little bit different. We're going to run through a simulated technical interview. Now I want you to think of this not as a test, but more like a collaborative problem-solving session. I'm really just here to understand how you think and approach challenges.
So, are you ready? Take a deep breath, get comfortable, and let's jump in. What I'm really interested in today is seeing your thought process. Remember, it's all about the journey to the solution, not just about getting the final answer right.
So, here's our plan for today. We'll start with a classic dynamic programming problem, just to warm up. Then, we're going to navigate a maze using a really cool technique called backtracking. We'll finish the technical part with a look at an advanced data structure, and after all that, we'll have a quick debrief. Sound good? Let's get started.
Okay, for our first round, we are diving straight into dynamic programming. This is a really powerful method for problems that have, smaller, overlapping subproblems. The whole idea is to avoid doing the same work over and over again. You solve each small piece just one time, save the answer, and then reuse it whenever you need it.
The problem we're looking at is the longest common subsequence. So what's a subsequence? Well, it's pretty simple. You take a sequence, you can delete some elements, or none at all, but you cannot change the order of the elements that are left. For example, if you have AGGTB and GXTXAB, the sequence GTAB is a subsequence of both of them. Our task is to find the length of the absolute longest one.
So that's the problem. My first question to you would be, how would you even begin to solve this? What's your initial instinct? The real key to any dynamic programming problem is finding those smaller, repeating pieces. So what do you think the subproblems are that we could solve here?
A great way to tackle this is with a recursive approach called memoization. Let's walk through it. First, you define your base cases. What happens when you reach the end of a string? Easy, the answer is 0. Then, if the characters you're looking at match, great, you add 1 to your count and just recurse on the rest of the strings. If they don't match, you have a choice. Either skip a character in the first string or skip one in the second. You try both and take the path that gives you the maximum length. And the most crucial step, you store, or memoize, every single result so you never have to calculate it twice.
Now let's see how this looks in code. This first line here, if ij greater than 0, this is the magic of memoization. Before we do any work, we check our cache. Have we solved this exact subproblem before? If yes, we just return the stored answer. Simple. If not, then we do the calculation. If characters match, add 1. If not, take the max of the 2 recursive calls. And right at the end, with C of ij equals q, we save that result in our cache for next time. It's that beautiful solve-it-once principle in action. Of course, this top-down memoization isn't the only way. You could also solve it from the bottom up using iteration, which is called tabulation. It's really good to be able to discuss the trade-offs. Memoization can feel more intuitive because it follows the recursive logic directly, but it might have some overhead from all the function calls. The bottom-up approach uses loops, which can be faster, but sometimes figuring out how to build the solution table from scratch can be a little less obvious.
Very good. That was a great look at dynamic programming. Now, let's switch gears for our second round and explore a different kind of problem. We're going to solve a classic maze, which is the perfect use case for a technique called backtracking. The idea is really simple. You try one path, and if it leads to a dead end, you backtrack and you try another way.
So here's the setup. We have a grid that represents a maze. Some cells are open, some are blocked. A rat starts at the top left corner, and its goal is to reach the bottom right corner. It can only move into open cells, and for this version, let's say it can only move forward or down. Our job is to find out if a path even exists.
The algorithm for this is a beautiful example of recursion. You start at the beginning, and you tentatively mark your current spot as part of the solution path. Then you try to move to a valid cell next to you. From that new cell, you repeat the whole process. You call the very same function again. If any of those recursive calls eventually finds the exit, that's wonderful. But if all the possible moves from a certain spot lead to dead ends, you come back, you unmark that spot, and you admit it was a wrong turn.
And if we look at the code, you can see this logic in action. First, we check if the cell we want to move to is safe. It's inside the grid, and it's not a blocked wall. If it is safe, we mark it with a 1 in our solution matrix. Then, we make our recursive calls. We try moving forward first. If that path eventually returns true, we know we've found a solution, and we just pass that true all the way back up. If not, we try moving down.
Okay, now this is the most important part. If both the forward move and the down move from our current cell fail to find a path, what do? We execute this line, sol xj equals 0. We unmark the cell. This is the backtrack. It's like erasing a wrong move on a puzzle. This single action is what allows the algorithm to explore other branches of the maze instead of getting permanently stuck down one bad path. It's the whole magic of the approach.
Excellent. For our final round, let's discuss a specialized data structure that is incredibly efficient for problems involving strings and dictionaries. If you've ever wondered how autocomplete on your phone works so incredibly fast, well, this data structure is a key part of the answer. Let's talk about the trie.
A trie, also known as a prefix tree, is a type of search tree. Now, what's interesting is that the nodes in a trie don't store the keys themselves. Instead, the path from the root of the tree to any node represents a prefix. For example, a path of nodes for C, then A, then T would represent the prefix cat.
So what is a trinode actually made of? It's really very simple. Each node just contains an array of pointers. For English, we can have an array of 26 slots, one for A, one for B, and so on. The only other thing it has is a simple Boolean flag, is end of word, which just tells us if the path to this specific node forms a complete word. That's it.
Inserting a word is a very straightforward process. You always start at the root. For each character in the word you want to insert, let's say cat, you just follow the corresponding pointer. From the root, you'll look for the C pointer. If it's not there, you create a new node and link it. Then you move to that C node and follow the A pointer, and so on. Once you've processed the last character, T, you simply mark that final node's is end of word flag as true.
Okay, so that is insertion. It seems logical enough. But the real power of a trie comes from its search capabilities. So let's say we have our trie filled with words. How would you then implement a search function? How would you check if a specific word, like explain, exists in our trie?
All right, let's pause there. Fantastic work today. We'll end the formal interview part here and just take a moment to debrief. We have covered a lot of ground, from dynamic programming to backtracking and finally to tries. Let's quickly recap the key takeaways from a session like this one.
When an interviewer asks these kinds of questions, they are testing for a few key things. First is pattern recognition. Can you look at a problem and think, this has overlapping subproblems. It's a good candidate for DP? Second, they want to see if you can analyze trade-offs, like we did with memoization versus tabulation. Communication is also huge. Explaining what you're doing is just as important as doing it. And finally, it all comes back to a solid understanding of core data structures, like the trie.
You have done a wonderful job today. This has been a great session. The goal of an interview like this is to grow and to identify areas for learning. So the question I'll leave you with is this. Having gone through these examples, what patterns or topics are you excited to practice next on your own? Thank you again for your time, and best of luck with your interview preparation.